In this new topic, we shall discuss a few tasks that may help you to keep your LC-MS instrument work continuously and minimize the downtime. I believe this topic is of very practical use, and specifically you will learn how to maintain your system, and if there is something wrong, you will know how to trace the causes of the problems. In this topic, we are going to use LC-Q12 as an example to discuss the maintenance and troubleshooting skills. While we are discussing Q12, we can add some similarities and differences when dealing with triple quadruple mass spectrometer. So specifically, out of this topic, there are very important two concepts you should grasp. The first one is mass accuracy, and the second one is mass resolution. So out of this topic, you should know how to calculate accuracy and how to calculate mass resolution. And you also need to know how to make adjustment if there is any accuracy drift or if there is any mass resolution loss, how you are going to do with your instrument. In Q12, there is a operation that you can do on a daily basis to bring back the perfect accuracy. This operation is calibration. So calibration, you can do it on a daily basis, but there is another one which can not only bring back your accuracy, but also can bring back your resolution. So this is what we call tuning. So these two you also need to grasp. And after this calibration and tuning, you need to learn a few basic maintenance tasks. So these few tasks will help you to prevent the instrument from contamination. I don't need you to memorize all the basic maintenance tasks, but you need to know for each of the tasks, is venting the instrument required? Okay, so for each of the tasks, you should know that. And lastly, we are going to learn some basic troubleshooting techniques. So this will take some time to give you the detailed workflow, how we troubleshoot for each of the issue that we may encounter. Before you learn the basic maintenance and troubleshooting techniques, let's first understand the structure of a Q12 mass spectrometer. I use Agilent 6550 Q12 as a model, but you need to note that different vendors have different designs to achieve high sensitivity and high mass accuracy. As you have already known, mass spectrometer detects charged ions, so the whole design of the instrument is meant to firstly generate ions, followed by ion transmission, and until finally ions being detected. Therefore, any design that is help ion being generated with minimized loss and also help transmit the ions to prevent ion loss, all these strategies are going to help to deliver high sensitivity. Moreover, for a specific TOF instrument, if the design achieves a better measurements of the time that ions are required to hit the ADC detector, it would improve the mass accuracy. So now if you look at the whole design of the Q12, it can be roughly divided into ion generation, ion transmission, and lastly, ion detection. In the next 2 slides, we are going to discuss how the specific design affects ion abundance, which is equivalent to, say, mass sensitivity, and also how the specific design affects mass accuracy as well. Using the same figure, we are going to look a bit closer at the whole design of this Agilent 6550 QTOF. So roughly, it can be further divided into ion generation, followed by ion transmission. After that, ion being filtered and fragmented. After that, ion will be focused to get ready to enter into TOF. Inside the TOF, ion will be separated and at the same time being detected. So this is basically the whole design of Agilent 6550 QTOF. So for ion generation, they use duet electrospray jet stream ion source. So what ion source is doing is to generate ions. Okay, so every generation of the QTOF instrument, they have done a lot to improve the ion generation. So what they are trying to achieve is that this high sensitivity. So usually you will see that the enhanced signal as compared to the previous generation of the QTOF system. Ion source, because it is located at the first part of the instrument, which makes it prone to contamination. Contamination in the ion source would affect both sensitivity and accuracy. So most of the daily maintenance tasks are related to clean up the ion source. After the ion source, ions will be sent to ion transmission, and there are 2 parts that are meant to transmit the ions: hexaball capillary and the ion funnel. These 2 parts, they are highly charged. So the reason why they are highly charged is basically to propel the ions to move forward. And also at the same time, they are going to get rid of those neutral molecules that happen to be introduced. Contamination in these 2 parts is also common. And the contamination will affect both sensitivity and accuracy. After ions being transmitted, we are going to see the first quadrupole filter. You have known the function of quadrupole. So the first quadrupole is to filter ions according to some parameters set in your method. So these settings are going to be used to select a specific mass range or to select a few particular ions. After the first quadrupole filter, we are going to see hexapole collision cell. As the name suggests, inside this collision cell, ions will be further fragmented. You have to understand, inside this collision cell, a very high purity nitrogen gas will be pumped into this cell, and the high purity nitrogen are going to collide with the ions to cause the further fragmentation of the ions. After hexapole collisions, ions will be focused by convergent hexapole and also slicer. These two parts, their main function is to make sure before the ions being sent to TOF, all the ions must start at the same starting line. The reason is, if the ions they start at a different starting point, the subsequent measurement inside the TOF will not be so accurate. So that's why the ion focusing is meant to make sure all the ions to start at the same time, at the same energy level. As you are all aware of, when ions being sent to the TOF, the time of different ions travel through the long flight tube will be measured, and the time will be converted to their m/z, and all these will be detected by the ADC detector. Alright, so this is basically the whole design of 6550 QTOF. Okay, this slide, you can treat it as a continued illustration of the function of each individual parts served for the whole QTOF instrument. And instead of using the figure to illustrate, I actually use some sentences to illustrate the functions. Before you actually read on the words, I would advise you to watch this video on YouTube. This might give you some better idea how the function of each part and how the better design to contribute to the high sensitivity and also high mass accuracy. So still, you will see the ion generation, as I have mentioned to you, the 6550 QTOF. They use so-called dual electro spray jet stream ionization technique. And using this technique, you probably see the mobile phase can be efficiently dried out. You probably will experience less background noise, and you probably can see more focused ion beam. So all this can contribute to higher sensitivity. Moving on to ion transmission. As I have mentioned to you, this ion transmission served by these major two parts: hexapole capillary and ion funnel ion sampling technology. And if you go and watch the video, you will notice they have claimed that using this new capillary, the intensity can be increased like 10 times, right? So the ion funnel, how the ion funnel actually can better propel the ions to forward. They say that the first stage of funnel can propel the ions forward while prevents the neutrons from entering. And then the second stage actually maintain the ion enrichment and focusing. And these two parts are also there. You can read on and just for your own information. Followed by ion transmission, you will see the ion being filtered using the quadrupole and also being fragmented using this collision cell. Just to remind you, inside the collision cell, collision gas is supplied by high purity nitrogen gas. Alright, moving on, followed by ion filtering and fragmentation. As you will see that ion must be prepared before they enter into TOF analyzer. So how they have been prepared before entering into the TOF analyzer. So there are a few parts that help the irons to be fully ready. So there are conversion hexapole, straight hexapole, iron beam compression guide, iron focusing lens, extractor, and slicer. So you can read on each of the function of the part, how they actually prepare the ions before entering into TOF analyzer. And inside the TOF analyzer, how the ions being separated by their M over Z. Inside the TOF, you will see pulsar, a mirror reflectron, and a fly tube, right? So as I have mentioned to you, if you look at your fly tube, and the material they use to made of this fly tube must be resistant to some temperature change, and this will help the mass accuracy. And the last one is the ion detection. ADC detector is claimed to can collect the data faster than the previous detector. So this is the same topic. It serves as a second part for this topic 2.2. In the first part, we have understood the structure of the QTOF. From this slide onwards, we are going to learn some basics, and that will help us to maintain this very expensive equipment. Logically, you should keep the logs of all maintenance, tunes, and calibrations. And you don't have to worry about this. Usually, for all the software, they should have an add-on and called daily logs. It will keep track of all the maintenance, tunings, and calibration that has been done to your instrument. But of course, there is a need to keep a log for your own routine maintenance, such as when you have cleaned up the source chamber. This wouldn't be tracked, so you have to manually written up somewhere. And when you have changed the reference solution, and also the tuning mixture, and so on. I believe there is another good practice. You can have a well-set method, okay, which can be used to monitor the overall performance of the QTOF. And so in this well-set method, you should have the mobile phase well indicated. What is a column? What is a gradient? What is the acquisition mode? Is it MS, or it's just a MS1? And a standard compound like recipe will give you some good indication on the performance of the instrument. So you can use this well-set method to monitor the performance. Usually you can do this on a monthly basis. If you know your instrument well enough, you will not be surprised someday the performance deteriorates. And some of the tasks, like what I mentioned here, you should do in a routine way. But some of the work can be done by the service engineer if your instrument is being insured under a certain agreement. Preventive maintenance, you can do it every half year, especially on the vacuum pump, because the pump are continuously working day and night, so some preventive maintenance is required half yearly. So for this vacuum pump, usually service engineer will help you to change the pump oil. And also, you need to clean the skimmers and octopole. Usually, these two cleanup you have to vent the instrument. You have to vent the instrument before you can really clean the skimmers and octopole, and this can be done on a yearly basis. And there is a divert valve. The rotor seal is a consumable. So you are supposed to change the rotor seal. If it's not done by you, must be done by the service engineer. And this can be done on a yearly basis as well. After all the tasks have been completed, you have to verify the system performance. The source chamber, or we call spray chamber, is located at the very front, so the contamination is very common. So you should regularly clean the spring chamber. Of course, how frequently you clean up your spring chamber, that will depend on your usage. And some good practice will be you should keep your tools and maintenance kits handy. They often will be used for other instruments, making them hard to find when needed. So you have to make sure you know how to locate your tools and maintenance kits. To ensure not only a functioning QTOF, but also accurate results, it is also essential to perform calibration and tuning for your instrument. So, what is calibration and what is tuning? Firstly, both calibration and tuning are able to bring back mass drift due to some variation of your instrument performance. Calibration usually is to correct minor mass drift, and what it does is to update the current tune file with a new equation that comes with new coefficients and so on. Calibration will not change any settings of optics and the electronics. In contrast, tuning can correct some mass drift which cannot be corrected by your calibration. And not only of that, tuning can also correct resolution loss. So this is a difference between calibration and the tuning. And it does change some settings to achieve the preset mass accuracy and the resolution requirement. So you will imagine calibration is more commonly performed while tuning is done less frequently. And likewise, calibration usually takes less time while tuning is more time consuming. And all the changes after performing either calibration or tuning will be updated to a tune file. A good practice is that there should be a backup tune file when your instrument was initially installed. Any further changes made to the tune file should be saved as a separate one. This is because at times tune file might be corrupted, and you should have a backup file to retrieve all the settings when instrument was firstly installed. In QTOF, mass accuracy is very important. That is why people in the first place choose TOF over quadruple. In QTOF, mass accuracy is expressed in units of parts per million, ppm. Calculation of mass accuracy is done using the following equation. The difference between actually measured m over z and the theoretical m over z divided by theoretical m over z multiplied by 10 power of 6 will give you mass accuracy in ppm. For example, for an ion, giving theoretical m over z equal to 622.02896 and the experimentally determined m over z equal to 622.02888,
the calculated mass accuracy in ppm should be as shown, minus 0.13 ppm. Please take note, there must be a minus or plus sign before the accuracy. 0.13 ppm minus 0.13 ppm is a very minor mass drift and nothing needs to be done. Some general guidelines in dealing with mass drift. If the drift is less than 10 ppm, usually no calibration or tuning is required. If more than 10 ppm, less than 100 ppm, calibration can be done to correct this. If more than 100 ppm, you need to perform tuning. But this guideline may suit for some cutoff, may not suit for all. You need to check with your service engineers for advice on the specific model. Other than mass accuracy, mass resolution is another key parameter that tells a lot on the performance of cutoff. Mass resolution is the ion mass divided by mass peak width. As you could see from this graph, for this peak of M of Z equal to 200 Dalton, its peak width is actually the peak width at the half height. We use W1/2 to indicate. For this case, the peak width is 0.5 Dalton. The calculated resolution will be 200 divided by 0.5 equal to 400.
Let's use this graph to understand a bit more of mass resolution. On your left, it shows a typical mass spectrum for 3 types of mass analyzers: single quadrupole, triple quadrupole, and ion trap. On your right, it shows a typical mass spectrum for other 2 mass analyzers, TOF and QTOF. The difference between these 2 are the peak width. The peak on the left is much wider than that on the right. That is why the 2 peaks adjacent to each other are close to each other on your left, these 2, and appears far away from each other on your right. If you calculate mass resolution, you will find quadruple type of mass analyzer gives a resolution less than 1000, while TOF type of analyzer can achieve 10,000 and above resolution. In fact, some TOF instruments can even achieve up to 40,000 resolution. You have learned mass accuracy and mass resolution. Naturally, you would think if mass resolution is high, the mass accuracy would be good as well. For the majority of cases, this statement should stand true. However, high mass resolution is not always leading to high mass accuracy. So we are going to use the following figures to show you 4 different scenarios regarding the relationship between mass resolution and accuracy. As you can see, mass resolution actually refers to how close each individual measurement to each other. If they are clustered together, it means there is high resolution. But the average of these measurements may or may not deviate greatly from the true value. This will suggest mass accuracy. If it is close to your true value, means high mass accuracy achieved. If it deviates from the true value, means poor mass accuracy. If you look at your figures, the figure 1 and figure 2 give you the clustered
measurements. So that means each individual measurement actually close to each other, which suggests good resolution. For the figure 1, the average of these measurements actually deviate from this true value, which means there is high resolution, but there is no mass accuracy. If you look at your figure 2, you realize the average of the measurements actually match very closely to your true value. Okay, so that means this is what we try to achieve: high accuracy and high resolution. Then if you look at your figure 3, you will notice all the measurements, they are scattered, they are a bit further away from each other. So we will say the resolution is not so good. The same happens to your figure 4. Resolution is not nice. But if you look at the average of the measurements, you will notice this average of the measurements is also away from the true value. So that means the accuracy is not good. While for the last one, even though you have low mass resolution, but the average actually match very well with the true value. So that means you still have achieved good mass accuracy. So this is basically the relationship between mass resolution and accuracy. Let's do this exercise to have a better understanding of the relationship between mass resolution and mass accuracy. Consider the theoretical m over z equal to 613.9588. Calculate mass accuracy for both detected m over z at 613.96 and 613.9569 on your right. I'll give you a few minutes to complete your exercise, then I will show you the correct answer. At the same time, you can also calculate mass resolution considering the peak width as shown above, 0.68 Dalton. On your right, that is 0.0423 Dalton. So recall the formula to calculate mass accuracy. The measured m over z minus theoretical m over z and then multiply by 10 power of 6. The answer should be 1.95 ppm and minus 3.09 ppm on your left and right respectively. To calculate mass resolution, considering the peak width as we have just described, recall the formula: m over z divided by peak width at half height. The answer should be 902.9 on your left, 14,514 on your right. This exercise demonstrates an unusual case that single quad, triple quad, and ion trap give slightly higher accuracy, although their resolution was much lower than TOF and QTOF. In
In this slide, I am showing you a standard calibration and tuning report. By infusing a standard mixture into this 6550 QTOF system, you will see this typical mass spectrum. Because the mass range was set between 50 and 1700, you will see 6 typical analytes. On the basis of each analyte, the software will calculate resolution and also accuracy in this table. When you are performing mass calibration, you come to this tab. You just need to click the button Calibrate. You will realize once you have done the calibration here, a new set of coefficients will be updated in order to correct some minor mass drift. In this slide, I am showing you a typical tune file. The red fonts are the ion travel path in this Agilent 6550 QTOF, starting from your ion source, ion funnel, to quadruple, until detector. All the settings are shown in this file, and this file should be kept intact in some folder which you can retrieve easily. In the source chamber, there are settings and actual readbacks. So this is a setting, while this is actual readbacks. Other actuals you need to note are at the end of the file. Such as vacuum for the rough pump. This is a rough vacuum. And your quadruple vacuum and your TOF vacuum. Vacuums gives a very good indication of the status of an instrument. Another parameter worth mentioning is the MCP value. When the detector was first installed, MCP value should be optimized and appear relatively low. When the usage of the instrument has become more frequent and the tuning has been regularly performed, MCP value will be gradually increased. The comparison between the installation value and the current one will indicate the performance of the instrument. This is the part 3 of the same topic. In this section, we shall discuss very briefly a few maintenance tasks. These tasks might be manageable by end users like us. We shall not touch on the tasks that can be best performed by the trained engineers. I shall use the picture showing the representative parts on which we would perform maintenance on daily, monthly, or yearly basis. There are 3 basic maintenance tasks. Source chamber cleanup. This will include nebulizer, spray shield, capillary needle inside the nebulizer. This cleanup can be done on a daily basis, and there is no need to vent the instrument. Another part that we could clean up is capillary cap and the capillary ion guide. These two are easily contaminated, which would affect the performance severely. After capillary ion guide, there is a skimmer. Its cleanup can also be performed by end users. To clean up capillary ion guide and a skimmer, we need to vent the instrument.
While leaving your instrument at standby mode, open your source chamber. You might see something like the picture shown. On the left, it is a typical ESI chamber. On your right, it is a typical APCI spring chamber. Very easy to spot the difference by locating the corona needle, which is only found in APCI chamber. To clean up the source chamber, a typical method is to prepare a mixture containing 50-50 isopropanol water, IPA water, in a squeeze bottle. You may squeeze the solvent mixture to clean up the parts. You can clean up the parts on your left. But you should avoid spraying the contents directly to the spring shield. This is a spring shield. Doing so, you might introduce large quantity of solvent to capillary ion guide, which is not advisable. To clean up the spray shield, you can use dampened lint-free cloth, which is usually provided by a supplier. You can also dismantle the source chamber and wash it using a large quantity of solvent mixture, 50-50 IPA and water. As mentioned earlier, you may use the squeeze bottle to clean the exposed source chamber. So you can squeeze to clean up the sides, but you should prevent the cleaning solvent from directly spraying into the capillary. So avoid this hole here. Without breaking the vacuum, you can remove the spring shield and the capillary cap will be exposed. Here shows the capillary cap. You may clean the capillary cap by dampened lint-free cloth. If you would like to remove the capillary cap, you have to vent the instrument. These nebulizers can be easily removed from source chamber for better cleanup. I have shown you the two different types of nebulizers. On the left top, it is the ESI nebulizer. On the left bottom, that is your APCI nebulizer. Inside the nebulizer, you will see a capillary needle. You can only see this tiny nebulizer needle through a magnifying glass. The protrusion of this needle would affect the efficiency of the dissolution process, so the protrusion must be adjusted properly. On the right bottom, there is a corona needle, which can be only found in APCI chamber. By removing the spring shield and the two retaining screws here, capillary cap will be exposed. After pulling the capillary ion guide and also removing the retaining screws, you can see skimmer in the next slide. Just to take note, the system needs to be vented before you can pull out the ion transfer capillary for cleanup. To thoroughly clean up your capillary ion guide, what you can do is you firstly protect the two ends of the capillary ion guide with 1 ml
pipette tips. You can cut off the tiny ending of the capillary of the pipette tip, and then you put on the two ends of the capillary ion guide, and then you can leave it in a clean measuring cylinder, and you have to put the special detergent powder and apply sonication for a certain period of time. After the cleanup by the detergent, you must rinse the capillary with ultra pure water. Any residue of the detergent will severely affect the performance of your instrument, so the thorough rinsing up with ultra pure water is very, very crucial. After you have pulled out the capillary ion guide, you may see the exposed skimmer. The picture shows the contamination which is caused by sample splatter. Cleanup of skimmer would require venting the instrument, and the solvent mixture can be applied to clean it up. This table summarizes the preventive maintenance checklist. It summarizes the frequency of each task. I have also stressed that for capillary and the skimmers, the venting instrument is required. This is the part 4 of the same topic, and this will be the last part. In this section, I intend to introduce the workflow of troubleshooting the Q12 instrument. I want to stress before we go into details that troubleshooting skills require lots of experiences. So in current modern society, troubleshooting has been mostly performed by engineers. We, as end users, usually would just make a call to their service center. For sure, we have gradually lost our motive and also our ability to perform troubleshooting. As we treat this subject from a more practical perspective, I would also demand less on your troubleshooting skills. More importantly, if you could manage the 2 exercise questions I have prepared at the end of this section, you are good for the basic troubleshooting skills. Common troubles you may encounter when using Q12 are sensitivity loss, signal instability, and resolution loss, or no fragmentation. And most of the times, the issues may entangle together. They wouldn't appear as an independent issue. So when you experience sensitivity loss, mass resolution might be lost as well. But for the convenience of teaching and learning, we have divided the issues as above mentioned: sensitivity loss, signal instability, resolution loss, and no fragmentation. And we are going to attempt each issue separately. You may read this slide and the next slide. The overall impression is that the vacuum is very important. So vacuum can be found as the root cause for nearly all issues. Therefore, an ideal vacuum is very important to have a working system. You may pause in this slide for a better reading. For sensitivity issue, you can check the current tune file against the original tune file to ensure the settings are within the acceptable range. A cropped file can happen. Using a new file may recover the sensitivity without any hardware troubleshooting. ESI emitter. For Agilent 6550 Q12, it usually only refers to the capillary needle inside the nebulizer. If the needle is not properly adjusted, meaning the protrusion is either too much or too less, this would affect the sensitivity. Contamination. is another cause for sensitivity loss. You may consider cleaning the source chamber, capillary ion guide, or even skimmer. Detector gain. This is more directly related to the previously mentioned MCP value. You may manually increase the value to bring back sensitivity, but do ensure you have ruled out other causes before you change MCP values. Insufficient vacuum affects sensitivity to a great extent. As said, incomplete vacuum will kill ion transmission. Check the vacuum gauges against the installation target value to ensure proper vacuum level for mass analyzer. For signal instability, you may check the capillary needle protrusion as well. Contamination in transfer optics would affect instability as well. Therefore, venting the instrument and cleaning the optics are necessary. Similarly, poor vacuum can also affect signal stability. The last one could be the syringe pump. If you are using syringe pump to perform calibration, it is necessary to check the syringe pump to ensure it is working normal. For the issue of the resolution loss, most of the troubleshooting should focus on TOF analyzer. Checking the TOF vacuum. If the vacuum is insufficient, it will cause resolution loss. And some settings in tune file will also affect the resolution. So checking the values against the previous file will rule out anything odd has happened. TOF analyzer requires high voltage power supply. You need to check voltage readbacks to verify the analyzer power supply. Of course, before troubleshoot for resolution, you need to ensure the sensitivity and the signal stability are within the acceptable range. For the issue of fragmentation, the most common cause is running out of collision gas. Collision gas is supplied by high purity nitrogen, usually in a separate cylinder. Ensure sufficient collision gas is present. Sometimes the settings of collision energy is improper. You may check these settings to ensure it is correct. No fragmentation might be also due to incorrect choice of precursor ion, which is related to MS1 transmission window or calibration. If the selection of precursor ions are incorrect, the fragmentation wouldn't happen. Collision cell sometimes has a separate power supply, so checking the power supply for collision cell might help address this fragmentation issue as well. Calibration. If calibration is not done properly, it will affect the selection of precursor ions. So at times you need to manually check by introducing a known standard. In this exercise, you are asked to answer the approaches in troubleshooting sensitivity loss. If you go back to slide 4, you will get answers to this question. I have summarized the approaches in bullet point form. Essentially, you need to check the source parameters, clean up possible contamination, check vacuum status, check MCP values, and also preparing fresh tuning solution. You may go through these bullet points to refresh what you've learned in slide 4. In this exercise, you are asked the consequences of poor vacuum. As we have discussed, vacuum is critical to ensure a working mass spectrometer. Poor vacuum would affect sensitivity. signal instability, and resolution. How vacuum affects these performances is because that poor vacuum would affect ion transmission, so that ions may be lost due to collision with moisture and air. In addition, poor vacuum in TOF analyzer would also affect ion travel path, leading to irreproducible M/Z. To sum up, in a more practical standpoint, troubleshooting a mass spectrometer requires a basic decontamination technique in the most accessible parts, such as the source chamber. Through learning the basic troubleshooting skills, you would understand the instrument better. Understanding your instrument will give you confidence in dealing with those small issues. I have added a few websites here. These videos may help you gain a deeper understanding how mass spectrometer works, how QTOF achieves sensitivity and resolution.